what he called the internal black hole. Was that the? Is he there?
Yeah.
Yes. So one point is that the point at the center is a conical singularity. It's not, it's like if you roll a piece of paper up into a cone.
Gerard, please unmute your microphone. Yeah.
Can you hear me? Sorry.
No, if you identify on the horizon at opposite antipolar points, then there's no cusp.
The point at the center is a conical singularity. Because
sorry?
The point at the center is a conical singularity. See, everywhere else you have a two sphere, but at the center you have a projective plane.
Oh, no, that is just projective because it is a seam of space-time with itself. So if I take two half spheres, I can just join them together. But if you make sure that at the joint, you make a 180 degrees rotation, or more precisely a reflection, so that you always connect the antipolar points, then there's no singularity.
But in the center, you don't have that.
That's what I do at the center.
Are you making a sphere everywhere, or is it a projective plane everywhere?
Yes, there's a sphere. No, there's a sphere everywhere, except at the center, where two halves of the sphere are identified, and therefore it's a projective at the center.
Yes, but I think that's a conical singularity.
No, that's totally regular.
Well, I think you find it's a conical singularity.
If you have a surface, if you have a surface connecting to another surface, that's totally regular, unless you connect the same transverse coordinates on top of each other, then it will be conical. But if you make sure that the transverse coordinates are different, then this connection has no local effect.
Well, anyway, the important point is not so much that. The important point is that you have to fit it onto an ordinary black hole. You have a collapse with a matter.
Not necessarily. The entire black hole is a four-dimensional instanton. You do this thing what I said in four dimensions.
It's an instanton.
You excavate a sphere. Sorry, yes.
It's in not four dimensions this time. Is that right?
Imagine the following: in four dimensions, you excavate a blob of space-time, say an S3 sphere to be concise. Although you might prefer other shapes, but that's a detail. So take something of the S3 topology and put that S3 in four-dimensional space-time and take out the interior. Now, I have a space-time with an interior piece lacking. There it collapses. So you identify opposite points and you make sure that only opposite points are identified to each other. Then I stitched space-time together again, and it's now a simply connected space-time. Now,
yes.
Now you split off the space component and the time component. So both space and time are getting inverted. So that's why I call it an
antipolar. An instanton, or is it space-time? I'm confused.
I'm describing space-time, but I put there an instanton. Instanton is just a topological configuration at some finite region near the origin, say, of space-time. And
but you might have the time t equals 0, it's part of space-time. Is that what it is? I don't understand in the picture.
Take a sphere where let's say t squared plus r squared is 1. Take that 3 sphere in space-time plus t squared plus r squared equals 1. Now the interior I excavate out, I throw it away, and then I take the antipolar points of that configuration and stitch them together. At every point, x is connected with minus x. Only at that point. It means that I've stitched. If you look at a small region, you can say take a small component of the space-time. It is stitched onto another component so as to avoid that you ever enter the inside. There is no inside anymore now. Can you imagine what I'm saying?
I don't understand what you're saying. I mean, the picture, what you call it, an eternal black hole, is that supposed to represent space-time or not?
No, it is basically a piece of space-time removed. You can do in a very simple, think of a line, remove a small line and then stitch the edges together again. Of course, you can do that. Now we multiply that with S2, then you can do the same thing with S2. You just excavate, you throw out a small segment and you glue the edges onto each other. That's all you do. Now, if the space-time metric would not continue precisely unless you take a conformal theory, but that all that are details. You can make sure that you smoothen the slight singularity of space-time, you smoothen it out. But that's not necessary in locally in the space-time. No, in fact, in your diagram, the Penrose diagram, then you can just say that these two regions are identified, and then you find that on the horizon they fit very snugly together, so you don't meet any singularity whatsoever.
Yes, look, I'm not sure I believe you, but let's leave that aside because it's not the important point. The important point is what is the relationship between your your eternal black hole picture and actual space-time. I mean, if I imagine a collapse of a black, say, take something like Oppenheimer's Snyder collapse, where you have an interior solution, and you then have it collapses through, and you have a horizon and all that. I don't see how that fits onto your picture at all. Where do you put the matter? Which
my picture now describes a small time fraction of the black hole. So imagine just 1 second of black hole. Well, a segment of say 1 second. During 1 second is much bigger than the radius, say, of that black hole, so that 1 second is already an eternity, but much shorter than the entire lifetime of a black hole, which could be billions of years. So take a black hole that has a lifetime of billions of years, take just a segment that is completely stationary in time. For the outside observer, it's totally stationary in time.
A section of it.
A section, a segment, a time segment of 1 second in length.
What coordinates are you taking for your time? Is that, I mean, which time are you taking? Because a black hole.
You could call it seconds. You can call it microseconds.
No, that's not my point. Is this a 3 slice through your 4-dimensional space, and then another one separated by seconds?
3 slices multiplied by a segment of 1 second for the outside observer. Then, in theory, that's going to be somewhat more complicated looking. But I just take your diagram now. Or here I have it.
But that doesn't. That's space-time. Is those diagrams I talk about are space-time?
Yes.
So where is the second?
Space-time diagram.
Sorry?
So let me see. Do you see it now? This is your diagram. That's space and time. So the time coordinates all coalesce at this point. This point at the center is like the North Pole on the Earth, say.
Yes, but in any model of a black hole that I know about, which arises from a collapse of material, that point is not there.
I understand that. So now,
if I draw the boundary
is more severe than that. This region has this thing has 2 asymptotic regions, this and that, as if it is a wormhole connecting 2 black holes. You understand that? You agree with that?
Yes, but
but instead of having another black hole, So
I think it would be nice
at first sight, it's
include
diametric.
I don't see anywhere where
At
you
first-
fit your matter into it. Where does the collapsing body? Where is the material of the body which
Collapsing body
collapses?
has been
to form that?
removed. The collapsing body is way outside because the collapsing body was 1 billion years ago, and the final collapse is 1 billion years from now.
But
So
1 billion
that's
years is in
completely
this picture
squeezed
because
on
the
this
whole-
horizon.
The boundary is infinity. So why 1 billion years is nothing?
Okay,
So
the
where is it?
ingoing matter should be on this line, but I took that out. On this line is the ingoing matter. On that line is the outgoing matter. I think you agree here that if I put that matter there, but then these two regions 3 and 4 are not there anymore. 3 and 4 are now replaced by flat space-time. So think of a shell of matter moving inwards along this green horizon. Then inside the shell of matter, there's flat space-time. I think you agree with that. So that means that 3 and 4 would be flat. Now, instead of that, I remove the ingoing matter because I say that's too long ago. For this observer, that's totally irrelevant when and how the black hole is being formed. And same thing in a very distant future. It doesn't matter for this observer
You have no
here.
room to join it on. I don't think your geometry makes any sense. I mean, if I were to draw the boundary of the collapsing material, okay, assume that was a long, long time ago, then that would hug that.
Exactly. But
Line at the bottom, yes. But how do you get through?
That would be very singular.
Yes, but that in that picture, you've got a joining onto a region at the bottom, that bottom triangle sitting on it's the singularity on the past.
Yeah,
how do you get into there? That's cut off by
a very legitimate question everybody asks, and I ask myself also, is how could this thing has been formed in the past? Because it looks, so what you now have to do is to say in the very distant past, there was the same thing at the side when the black hole is still very, very tiny.
But the very distant past should be on your picture. It should be that line going from the bottom right-hand point to the top left-hand point.
I'm now doing something else. That is to say, I've removed the ingoing matter and the outgoing matter. Because there's also
I don't see what you mean by removing it. That's a different model where there is no ingoing matter. Is that right?
Let me say it this way. Suppose you consider an atom that was formed somewhere by some process during the Big Bang. Now, I don't care when I look at an atom, I don't care what happened to it during the Big Bang, because that's too long ago. I want to understand the atom now. Same thing for the black hole. I'm not interested in how it was formed, not interested in how it will decay in the end. I just am interested in right now.
You can be not interested in it if you like, but it's still there.
Probably it would be nice to include other people in the discussion. So I will not change topic, but I think Philip has a comment on this. So maybe we can include him as well, and then go back to the two of you.
Whatever.
Okay, I don't have any contribution to the current discussion. I had a question to Roger from his presentation earlier this morning. Couple of points. One is a small point, and the other is a bigger point. The small point, I've been thinking a little bit about what happens to the superposition principle when you have two sources. Now, from the gravity viewpoint, the only reason you have superposition of potentials is because you can linearize, and the Poisson equation is linear. But if you have two sources and you calculate the metric due to both of them, the total metric is not the sum of the two individual metrics. Because
no way I didn't say it was. No.
So therefore, the superposition of Newton is sort of a little bit of an accident from the perspective of general relativity. But the superposition of quantum mechanics is very different. And what happens is the center of the wave packet takes the classical trajectory, but the wings of the wave packet don't. So if I have two Newtonian sources and I just look at the geodesic, it will be the geodesic of adding up the two potentials. but the wave packet doesn't stay on the geodesic. The wave packet leaks into the other paths. And that's why I think the quantum mechanical superposition principle is in conflict with the Newtonian gravity superposition principle. Anyway, that's my comment on that part of the two sources. Now, going back to one source, the thing I did mention before about the Colella-Overhauser and Werner effect is you split up in an interferometer a neutron into two different pieces. And then when they recombine, you get a fringe shift. And that's because they're coherent. And what that's showing you, and the fringe shift, of course, was due to the gravitational potential in the interferometer. And what's that showing you is that gravity knows about quantum mechanics. And I think that's why I thought that was the more important point. I think once you start off by recognizing that gravity knows about quantum mechanics, you don't have any choice but to figure out a theory of quantum gravity. It's not that you'd like to. I mean, I think that experiment is telling you that you have to, not that it's...
Philip, if I may say something, sorry to interrupt, but Colella-Overhauser-Werner experiment doesn't say anything about quantum nature of gravity.
It says that gravity knows about quantum mechanics. I didn't say that gravity was quantized. It's the quantum mechanics of the neutron in an external classical gravitational field. And you're still getting a fringe shift. In other words, classical gravity is causing a quantum mechanical fringe shift on the neutron. Now, then I said, if that's the case, if gravity is coupled to matter and matter is quantized, and gravity knows it, there's no choice but that gravity would have to be quantized too. I didn't say that the experiment was an experiment of quantum gravity. So that was the comment on that experiment. Now, if I can just take another moment, is to comment on the general program that you've described. You drew a picture where you merged the quantum mechanical loop with the gravity loop, and you said, well, in the overlap region, would we have to make a change on both sides? And I've been working precisely on that. I don't regard the changes as radical, but I can assure you my colleagues do. On the gravity side, the only thing you need to do is to impose a principle of conformal invariance, and then the gravity side becomes fourth order conformal gravity. When you quantize that, you run into what you think is a ghost state. However, the real thing that the issue from the quantum side is finding the right inner product. It's certainly true that the Dirac norm, namely the overlap of a state with its Hermitian conjugate, would be negative. But there's another norm, which is the overlap of the state with its CPT conjugate. And that one is positive. And so you make something of a change in the gravity side. You stay metric. It's a covariant metric theory of gravity. You impose an extra principle, which uniquely selects the action. And on the quantum side, you change the inner product. And that's I don't regard that as radical. My collaborator and good friend Carl Bender is the one that's been promoting this within the so-called PT theories. But I don't think that's in any way radical. That's an allowed property of quantum mechanics. It's not a change in quantum mechanics. So I think that's the sort of the minimalist thing you can do. Certainly, at this conference, we've heard a lot about these very complicated, infinite dimensional actions. And I think that's much more radical than just having an action with one term in it. So anyway, those are my comments.
Yeah, but I don't think it addresses the questions I was raising. I mean, I think you have to do something much more radical. I mean, quantum mechanics has its problem anyway, namely the measurement problem. And do you regard that not as a problem, or what?
Well, let me say two things. One is, I don't think it's necessarily gravity that has to solve the measurement problem.
I agree with that. It doesn't, from that point of view. You see, I'm presenting an argument which addresses that question, but usually, if you don't have gravity, well, nobody I don't think you have to have my model to have a resolution of a measurement problem. I agree with you there. It doesn't have to be gravity. So that's another point of view. But I think that if you consider that it's gravity, you are led in a certain direction, which is helpful.
Okay, well, can I make a comment which is, even by my standards, I regard as radical? When I worked through the pure fourth order theory, I discovered that the graviton has zero norm. And I've even suggested that the measurement, the collapse of the wave function is actually the emission of these extra zero norm states of gravitons, which are not detected. That's about as far as I've been able to get on the measurement problem. That actually there's a piece that we're simply not seeing because it doesn't register in a detector. But I'm not prepared to make too much of a case for that idea at the moment.
The Colella, or that Colella, etc. experiment, yes. I mean, that one's just using a fixed gravitational field, so there's no issue in relation to what I'm saying there. Yeah.
Yes, what they do is they take an interferometer in the horizontal, and then they rotate it into the vertical. So the upper arm of the interferometer is at
I know the experiment. Yes, I know. But that's you only have one background gravitational field. I mean, I was saying that's perfectly consistent.
Yes, that's true.
Yes. That's what I was trying to say. It's still consistent at that level. It's only when you try to make a superposition of two different gravitational fields that you have trouble.
Yes.
Perhaps Gerard wanted to add something.
Yeah, just a small remark, which is that I've just sent a paper to the archives where I claim that quantum mechanics itself can be very easily understood in totally classical terms if you do it right. And most people apparently don't, but you can understand quantum mechanics as a purely statistical description of something which also in its pure form without statistics uses the same mathematics. And that way you avoid the measurement problem, the collapse problem, and even the EPR difficulty, although that's more difficult to understand what really happens there. But in fact, all these problems can be basically removed if you view quantum mechanics that way. And I'm hoping one day we'll be able to add that to the whole picture of black holes and other problems with quantum gravity, just to understand how the world hangs together. But our big problem, of course, is to find any set of local equations that does the right thing. And we're all here trying to figure that one out. It's very, very difficult. But I hope that by looking differently at what quantum mechanics is, that will help a lot.
So Gerard, if I may ask you, so then, so what's the difference from your perspective? I mean, from the normal quantum mechanics to your version of quantum mechanics, what will be the crucial difference?
There actually is none, because ordinary quantum mechanics can be expressed in this novel form, except that you have to say that at very high energies that we can't reach today with any of our accelerators, things happen that you didn't expect. Which is the very high energies, things start to behave classically. But in spite of them behaving classically, you can still put them in the energy eigenmode. But if these particles are so heavy, the only energy eigenmode open to them is the zero state, zero energy state. So all these very fast moving variables at very high energies, they are sitting in one single quantum collective state, which is a super coherent state. But if anything else interacts with that, then all the ordinary classical interactions you might think of then automatically turn into quantum mechanical ones. So quantum mechanics just comes out of the theory without having it really put in, except as a tool to do calculations. So perhaps the difference between my quantum mechanics and the way it's usually done, usually quantum mechanics is considered as a theory of atomic and elementary particle interactions. I replaced the word theory by the word tool. It's just a powerful mathematical tool that enables you to do statistics, where under ordinary circumstances you can't do that. So that's the difference. And that mathematical tool is extremely useful for anything in physics. So that's why
But-
quantum mechanics become so powerful.
In principle, you would be able to explain the superposition, spatial superposition, which people have already
Superposition is
seen
just-
in the board.
Superposition is just a mathematical procedure. What it boils down to is that you don't know which state you are. So you write down a superposition. And
But
so
people have seen this in the laboratory. So, like the Vienna, the group of Zeilinger, where they have done this kind of experiment to put, this bucky
yeah,
balls.
that's what they say, but it's not quite, well, I have lots of things to say about that, but it has to do with the fact that, okay, you might say my proposal has one, what you call a weakness, you might call it a weakness, I just say it's a phenomenon, a feature rather than a bug. But the feature is that you first have to choose a basis. Now, since we want locality, as a basis, I would use the fields of a quantum field theory. That's completely local. So those fields are now stripped from their quantum mechanical meaning and we replace them by classical fields, which physically doesn't make any difference because they all commute with each other. At the space-like surface, a Cauchy surface, all the field variables commute. So replacing those quantum mechanical ones by classical ones has physically no effect. But now all the other things become operators. And you can understand that if you add fast-moving variables, which are forced to sit in their lowest completely coherent state, the zero energy state. The low energy particles can be in any other state. And then you get real quantum mechanics out of this, not an approximation or anything, just real quantum mechanics with real statistics. The Born prescription is the only prescription left over to understand what you are doing. So quantum mechanics comes out. It actually wasn't put in differently than as a tool to do calculations.
But how does spin and a half fit into this?
Spin and a half are just flip-flops. So they're just a degree of freedom which only flips over from two values 0 and 1 all the time, dictated by other variables that tell them when to flip. So this you can see as a consequence of indeed flip-flop interactions, which can be completely classical. A classical flip-flop is just a thing that has 2 degrees of freedom and it may turn over as soon as you touch it like this. And but then in quantum mechanics, you can attach states to that. And you use anti-commutation again as a tool to be able to handle the mathematics, just only for that, no other reason. And this way you can build up exactly the world like we know it today. But the advantage of this is that you take away much of the mystery. There's now no longer any physical sort of secret to what quantum mechanics means or something. It means nothing. It just means we've addressed the very complex equations of motion that are still classical. We've addressed those by using Hilbert space just as a method of doing calculations.
So I think this philosophy goes very well with your the black hole case. Again, this
goes very well with black hole, yes.
Essentially, what you are saying is that there is no S matrix. So in principle, you can do quantum mechanics.
No, there isn't. There is an S matrix. There will be an S matrix because I really generate real quantum mechanics, and real quantum mechanics also has an S matrix. So I'm not against S matrix theory, far from it, but I'm saying that you understand the S matrix if you know how to integrate the equations of motion. Like when you do a scattering experiment with particles, it's a complicated calculation from the Schrödinger equation to find the S matrix. Of course, but a good physicist, if you have the right kind of models, you can do such a calculation. But that's fine. So you can do the same calculation in the procedure which I just sketched. In fact, it also goes remarkably well with string theory. String theory, the basis of string theory are just discretized string bits of a given length just moving around. It works in a very interesting way for strings as well. So, which means that you start at a completely finite theory with discretized states. And then on those discretized states, you build yourself mathematically a Hilbert space. Has nothing to do with the physics. But then you discover that the Hilbert space generates for itself a Schrödinger equation to explain the evolution. And you are left over with real quantum mechanics. That's the way things go.
So essentially, in your picture, would there be no entanglement, or would there be an entanglement between two
Oh, there
systems?
could be entanglement because it's just a probability. I mean, entanglement just means that you have rather complicated dependent probabilities in the states. You can still think of entanglement, but I'm only allowed to use a basis for everything. On the basis, everything commutes. And that you would call a restriction, but in quantum field we're very close to having such a basis. So we shouldn't, in principle, we should not worry. But I'm sure all of you are worrying about such a drastic proposal. And of course, I worry myself a lot. It took me a long time to reach this point that I now really start to believe that this is the correct way.
But maybe here is this difference, because in entanglement, you build up precisely because of some off-shell interaction. So there has to be some kind of like an interaction. And if I switch off the interaction, then I switch off my entanglement as well.
Entanglement has nothing to do with interactions. In principle, you can have much more entanglement if you have no interaction. Because entanglement very often spoils, it splits the energy levels. Only if you have degenerate energy levels, you can have entanglement. But entanglement basically is just an example of particular superpositions. Now, every superposition has its Born interpretation in terms of probabilities. No matter how you superimpose things, it is a probability distribution in terms of the things at the basis, or at a ontological basis, as I call it. Everything commutes. It's just ordinary probability. But as soon as you make a unitary transformation, it's your responsibility, but it lies there to be picked up, that you can make unitary transformations. As soon as you do that, you have real quantum mechanics, and you don't understand anymore what you're doing because your basis elements themselves are no longer ontological. So when you superimpose those again, you're doing things that are very complicated mathematically and physically even more difficult to understand. But if you look very carefully, you see it's nothing but probability distributions, classical probability distributions, complicated, interconnected probabilities. So you could say entangled probabilities, but it's no different anymore from classical atomic theories, from van der Waals gases or whatever.
So, thanks. This was very interesting. I see from the chat that people are suggesting to go back to some topics more related to today's talks. So does anyone have a question to some of the speakers of today, or otherwise we can continue?
No, I think there were some questions to some of the speakers in the chat, yes. So
yeah, but I don't see anyone now.
No, maybe, yeah.
I'll ask a question to Roger, if I may.
Sure,
yes,
sure.
Yeah.
And are you not surprised or perhaps worried about the fact that in cosmology, the by far more dominant state is the vacuum state, and there are only very slight excitations of the vacuum. There are billions of states you can form in principle, which contain much, much more particles. But for some strange reason, nature chose to be extremely selective, that the state we see in the universe is so very close to the vacuum. Have you thought about the question, how come? Why is that? Why don't we have as a half full bucket of matter, but rather why is it so that the matter that we have spilled out in the universe is so thinly distributed over the universe? Why is that? What would be the origin of that?
I guess I don't understand. It changes, of course. It's very, very almost a vacuum in the remote future, but very concentrated in near the Big Bang.
Yes, for very short moments during the Big Bang, the universe was very small, and it may have been indeed filled.
But I'm trying to argue that it's very similar, because when you have no mass, and then the conformal picture makes sense, and they are very similar. That's the point I try to make in my picture.
But even in those conformal theories, aren't you very close to a very even, very flat, very featureless configuration in our universe, where there are only a few particles around, relatively few, that cause a very little bit of curvature. But well, I'm asking the question because in my way of formulating quantum mechanics, I can just well fill all the energy levels, and I can take instead of the lowest energy level, which is the vacuum state, I can take the highest energy level, which is the complete dual opposite of the vacuum. It's a completely filled state. And to me, there's a perfect symmetry between the completely empty state and the completely full state. So now, but now the question is, why is a completely empty state so very close to what the universe is, the way universe is acting today? And why is a totally full space remotely separated from any state we can generate, even in accelerators?
I don't understand your question. I mean, it starts very full, if you like, and it gets emptier and emptier as the universe expands. And then it gets very empty in the remote future. Now that's the normal picture. Now, of course, my picture is trying to say that the state at the very beginning of the eon, as I'm going to call it, is very similar to the state at the very remote future because they're conformally equivalent.
Yes.
But it's not as though I'm saying that they're very, I mean.
But it looks, the problem with that, of course, it looks very much like nature being not conformally invariant at all. I mean, every atom has a particular size and particular mass, which
none of it's massless.
again conformal
Yes,
symmetry.
well, sure, it's the mass that gives you the scale. If you didn't have mass, that's the whole point. If you don't have mass, then you don't have the scale. But as long as mass is around, then it defines how big it is. But in the very early universe, the point is that asymptotically, as you go back to the Big Bang, the mass becomes less and less relevant because the energies get so large that the kinetic energy dominates and the actual mass of particles becomes irrelevant. So that at the beginning, it is very like a conformal situation. And the remote future, again, it becomes like a conformal situation, but only if you can somehow get rid of the mass. Now, a lot of the mass is got rid of because a lot of it is photons anyway. And certainly if they get swallowed by black holes, then the Hawking evaporation turns it into photons. So you have primarily photons, but you still have some mass around. So the argument I make is that you do need something in addition to current physics, which is that in the very remote future, the mass decays away. And part of the argument has to do with the Casimir operators. You see, when you have a dominated by the Poincare group, you have the Casimir operators of spin and mass, and these are absolutely conserved. But when you don't have the Poincare group, but you have something much more like the de Sitter group, then you find the Casimir operators are different, and mass is not a Casimir. So at least it's more plausible that you could have mass fade out in the remote future, but I agree that the mass fading out in the remote future is something which one doesn't have in normal theory. And so this is a hypothesis which one might argue about, but it is a hypothesis of the theory.
A different way of phrasing the problem is that you can take the determinant of the metric tensor and observe that is a dynamical variable, very much like the gate field in the gate theories.
What do you mean by the determinant of the metric tensor?
Well, the metric tensor consists of locally of 10 degrees of freedom, right? The 10 components of a 4x4 symmetric matrix. There's one particular combination of that determines the determinant of the G mu. So the determinant of G mu is one of the 10 degrees of freedom, say, of the metric. But that you can gauge to 1 by choosing your coordinates. Right?
It's just the determinant has to do with, no. Yeah, it doesn't mean anything. The determinant of the metric doesn't mean anything. It's just a...
Well, you can choose your coordinates such that the determinant is always 1, for instance.
In other words, it doesn't mean anything.
You might, I don't like that gauge, but you could choose that gauge if you want.
Yes, well, yes, but that's just a coordinate change. That doesn't mean anything.
Yeah, well, what you have is now the mass of an atom or a particle or whatever has to be compared to that determinant. Without that determinant, you wouldn't know how big the mass of a particle is. So basically,
It's
what
not
we
a
call
number, in
mass
the sense
is
of a
actually
pure number. I don't understand. But it's a,
what we normally call mass in a particle theory is mass, or is the mass if you put that determinant fixed to be 1 or something, or -1, but fixed. And with that, once you know that, you can define the mass of the particle in terms of the equations. Otherwise, you have to put the g mu in the square root of g, you have to put in. So in the action, there's square root of g everywhere, where g is the determinant of g mu.
that's how you write things, but yeah, I mean,
And,
that's just coordinate effects.
without that thing, the theory would be wrong. I mean, you must always multiply all massive component things in the equation of motion by the appropriate power of the square root of -g.
That's a question of how you write things. That's not a,
Of course it is, but
I mean, it's just a question
can
of what your
also-
coordinates are used. I mean, you can choose coordinates so that you make that square root equal to 1 if you want to, but it's just a coordinate.
yes,
effect.
but
It's not-
but you can also observe that that thing is a dynamical degree of freedom, because when you choose your coordinates differently, then
Well,
then
there's
the thing
something that doesn't
can
mean
be just
anything.
and vary.
I don't understand. I think we
Well,
talk
what
about
I'm trying to
this
say
about
is that there's an intrinsic conformal symmetry in pure gravity as well, but just if you recognize the square root of g mu to be a dynamical variable, which in a certain sense it is.
But that's a coordinate effect. How can a dynamical variable be a coordinate thing? I mean, I'm interested in the physical quantities.
The symmetry of nature is a symmetry where you can perform any coordinate transformation, provided that the metric tensor g mu is transformed accordingly. Right? You cannot go to other coordinates without adapting the metric tensor g mu. Same thing for the square root of the determinant of g mu.
It's just how you write the coordinates you're
If
choosing.
coordinate transformation that blows up a volume, then you have to take care of that by putting factor square root of -g everywhere.
But you need something else than the metric. I don't understand. Sorry.
Well, it's a question of words, and what you don't understand is the wording. But of course you understand the physics like I do. But I just say that you can reword the physics in such a way that conformal symmetry is there and is already spontaneously broken. The spontaneous breaking means that the value that you want to work with is not that square root of g is 0, like you do in many gauge theories, but the square root of -g is 1. And choosing that 1, you could choose it 12, you could choose it 39. It doesn't matter, but you give it a choice. And the same thing happens in the standard model. The Higgs field has the same job. You can turn the field to 0, that doesn't make much sense. But you can take the z component of the Higgs field, or one of the components of the Higgs field, you can put that equal to 1, although we often choose a different number there for convenience, but you fix the value of that field. And then you find out that you get this famous Brout-Englert-Higgs mechanism that generates the masses of the other particles. So, but then there you compare this with a spontaneously broken symmetry. In the same sense, in gravity, you can also compare the conformal factor with a spontaneous broken symmetry and say that we have a Brout-Englert-Higgs mechanism in gravity automatically without changing any of the physics. The physics is just Newton's, the Einstein-Hilbert action period with ordinary matter fields. But the language you can modify. The language is, you can call that a spontaneously broken conformalist invariant symmetry. So when we talk about mass, we actually talk about mass chosen in the appropriate coordinates. If I use centimeters, the mass of the atom is much smaller than if I use nanometers. So the mass of an atom itself only means something if you at the same time specify what the square root of the determinant of the metric tensor is. So it's a relative quantity that's physically important. But that relative quantity has changed during the evolution of the universe.
I think we talk different languages. I mean,
yes,
to me,
to deal with the topic, and also can we also focus on the talks today? about black hole solutions in fourth order gravity. I think we have a lot of questions also discussion is going on in the charts as well. Yeah, I mean, well, I have a question to the Bob's talk. Basically, he has discussed the two-to-hole solutions, which are singular, but there are other class of solutions like 0-0 solutions, which are non-singular. Why two-to-holes are more interesting than 0-0? And we would like to resolve the singularity, right? In general. Bob, yeah.
Well, the non-singular solutions do describe stars and everything else that we know of, except for black holes. So of course they're the important solution. But for black holes, it doesn't work. So in our study of the numerical solutions, we could see that as we put more and more matter into a certain region, the 0-0 solution stopped becoming a solution, and the 2-2 solution started to become a solution. So they're disjoint. They weren't both solutions at the same time.
So you say that these two solutions are disjoint? I mean,
yes, the non-singular solution only existed when you did not have too much matter in a region.
Okay. But in one of your work, you're kind of trying to join these two solutions, right? In some region, you have 0-0, and in some other region, you have 2-to-hole solution. Maybe if I'm
sorry,
no, I'm saying in one of your work, you are joining these two solutions. That means when there is a lot of matter, you have 2-to-hole, and then when you go away from r equal to 0, so you are connecting it to 0-0 solutions. Am I correct?
They're both solutions of the same theory. Yes, but that's all.
Okay, so there is no connection between them. So these two solutions.
Completely different solutions of the same theory that correspond to having different matter densities.
Okay.
Any other question?
Could I bring up, I guess Gia has gone. So I don't know whether the thing I'm talking about fits into his picture of what happens when you have E plus E minus colliding with a lot of energy, and which he would say gives rise to a black hole. I mean, in my case,
this is a calculation you can do. If you take 2 point particles, with an enormous amount of energy, you let them hit head on with impact parameter 0. I'm sure they make a black hole. It's very difficult to calculate the details here. You have to do it numerically.
In my talk, I was talking about holes in space-time instead of black holes. So the collision could produce a kind of a hole, and without all the entropy of the stable solutions that I was talking about, just some kind of hole that would form and then be unstable and then just decay back into normal vacuum. So it might be that this picture is will have a different result.
If I could channel Gia, with apologies to him, I think he did comment on that point. The higher derivative theories that you're talking about, insofar as they're asymptotically free, would not obey the kind of physics that he's talking about, so they wouldn't necessarily classicalize.
he seemed to be more strong with that, with his statements afterwards. So I'm not sure what he would say now. But
Sorry, he did say that. He did say
Yeah.
that he would not expect that to go on in an asymptotically free theory.
Okay, that's the basic question I would like to ask. I mean, for example, do you agree with that?
Do I agree with Gia's basic idea that that in Einstein gravity or anything with positive energy and positive norm, that when you scatter together two things, that the interactions become non-perturbatively strong, and that they effectively classicalize through the formation of a black hole? It seems plausible. I don't accept that it's been proven. Again, I know he is going to attack me for that, but it certainly seems plausible. And I would love to explore the implications of that for loop amplitudes. So he's talking about scattering amplitudes, but you could ask, loop amplitudes, when you put virtual particles together, is somewhat similar to that. And one might wonder not whether that's going to cause the loop divergences that we encounter to regulate themselves. I don't know what his opinion on that is, but I think it's at least possible. It's at least plausible. It's been suggested, since before you and I were born. The people who played around with quantum gravity in the 1950s speculated about this. Nobody has ever been able to do anything with it.
But the picture of black holes as a huge clump of soft gravitons, is that close to reality or not?
I think it is missing, at least, because why just gravitons? I mean, we have all sorts of matter. We have neutrinos, electrons, and so on. So we should, whatever you put together can make a black hole. You don't have to make use gravitons at all. I know people like to think of gravitons forming black hole, but I don't see a good point there. You can just take anything, collide any point-like particle with any other point-like particle, have enough of them, and you'll get a black hole.
Yeah, I think that's obviously true. Gia, for some reason, kept saying that we need to model de Sitter, and I think you also would say black holes as superpositions of gravitons, but it seems to me, maybe he meant virtual gravitons, the things that would, describe the constrained, what I would consider to be the constrained components of the field rather than the dynamical gravitational components. But I agree with what Gerard said.
My favorite is to
for an asymptotically free
black hole with a bucket of. Sorry.
I'm just asking, in the case of an asymptotically free theory of gravity, could this basic picture of black hole production change?
Well,
yes, I think it's certainly.
I think it's a bit naive to think that would be an asymptotically free theory of gravity, because that limit would be totally different from the Einstein-Hilbert action. And so therefore you cannot be close to any perturbative theory that we know of. So I don't think gravity can possibly be asymptotic, not in 4 dimensions. In 2 dimensions, yes, but not in 4, I don't think. Because we don't have any theory that can represent its very high energy behavior.
Well, I described quadratic gravity as an example of a theory.
Yeah, but then you have, of course, all the negative metric objects. Of course, yes, you add higher derivatives like we've been doing all the time here. You can you can say that, but then you have, well, I think it's still a sick high energy limit with the wrong metric everywhere and the wrong energies. I'm very hesitant to accept such a theory as a plausible or useful asymptotic limit of any theory, including gravity. Or someone has to come with a much better motivation than anything I've ever seen to convince me that that would be a good candidate for an asymptotic description of gravity. It's much more likely that we have a lattice of some sort.
There is a question from Tomislav.
Yeah, hello everybody. Yeah, I have a question to Gia, and if he's not here, I would also like to ask opinion anybody who might have one. Namely, I very much appreciate, and I think I understand what Gia is trying to say when he talks about coherence proposition of gravitons, in particular in black holes in the sort of saturated state. But of course, take, for example, the moon, right? The moon generates its gravitational field.
I'm sorry, I didn't hear that word. Take
the moon, just any object, right? The moon generates its own classical gravitational field, which also can be thought of as superposition of all-shell gravitons in the sense that Gia is talking about. So my question is just the principal question. Is there also some kind of finite, it can be huge, of course, but finite time by which, due to these kind of scattering effects Gia is talking about, the classical description of the gravitational field of the moon will stop being classical? Does anybody has any opinion about this? Because I do understand, yes.
You can ask the same thing about electromagnetism, about photons making an electromagnetic field. Conceptually, that's somewhat easier, but...
yes. I mean, it should be the similar question, right?
Of course.
I suppose we could wonder about whether there would be a very, very unlikely oscillation that would cause the moon to collapse.
Right. So the question is, yeah, I think it's a well-posed question and probably has a good answer. And I suspect that it also has something to do with somehow the gravitational fields and matter fields arrange themselves to minimize locally the energy functional, right? I mean, the energy locally, but also the energy functional. And the question is whether this energy functional being minimized poses certain constraint on the quantum effects and what they can do to destabilize this configuration. Because of course, for the moon, if it is moon alone in the whole universe, it's asymptotically, you know, Minkowski space, so everything is well defined there, right?
We have to admit that we don't know the exact local theory of nature. We don't know what the physical degrees of freedom are. We don't know what the equations of motion are. We only have all sorts of limits. The moon is one limit. A bucket of water, which is my favorite, would be another limit. And the black hole, as far as we understand it, would be also a limit. Maybe there are more interesting limits to consider.
Yeah.
Well, like a plasma theory of a neutron star or whatever. But many of these are simply out of reach for us today. We don't have the full equations.
Yeah, but I'm suggesting a thought experiment. If somebody can construct a thought experiment which would say whether the decay time of the moon gravitational field is finite or infinite. You know? So,
well, that would be the decay time of the moon itself. And you know very well, the moon probably will outlive us for some time, but then after a while it will just disappear.
Yeah, because of the influence of other gravitational fields and other objects, etc., right?
It'll be swallowed by the sun quite. But,
yeah, but if it was a sole object in the universe.
Yeah, I said about black holes and about everything.
Yeah. No, but black holes, of course, they have a different, you know, they have other conceptual issues. that are hard to deal with, while the moon's gravitational field, everything is well defined, everything is weak field limits, no singularities issues, you know, all of this is much simpler.
Well, the only
I think the way that you'd have to work it is to look for a very, very rare fluctuation where the moon, the mass in the moon, or enough of the mass in the moon underwent a very, very rare fluctuation so that it got within its Schwarzschild horizon. That's obviously hugely unlikely, but in the fullness of time, maybe it would occur.
Right, right.
There is a question also from Sravan for Roger.
Oh, hello. Yes.
Maybe. I have actually two questions. The picture of cyclic cosmology you have presented, does it fit with the inflation? I mean, is there any period of inflation in that picture?
Inflation has to be not there. You see, inflation, I argued that inflation does not smooth out the universe, but nevertheless, the usual argument is that inflation is needed to explain the scale invariance of the microwave background. Now, if you don't have inflation, it would ruin my picture if you had inflation, because it would extend the distance between one eon and the next, so you would have almost no communication whatsoever, because inflation would simply scale the gap between one eon and the next to an enormous factor. I never liked inflation. I never believed it. It doesn't smooth the universe out. It would have the effect of having the scale invariance that people want for the temperature variations in the microwave background. So you need another explanation for that if you don't have inflation. The other explanation for it in my picture is, I didn't go into this, but you see, when you look at the equations, when you cross over from one eon to the next, you find that you have to create a new material which is completely gravitational in its nature. And I conjecture that that is dark matter. You have to have it. Basically, to hold the universe together, to be so small, it has to have a content which is a scalar material which interacts only gravitationally. Now, I claim that that is dark matter. Now, in order that the dark matter does not build up from eon to eon, it has to decay away. So it has to decay, and it decays into some form of gravitons. Exactly the nature of that decay needs more thinking about. But the fact that it decays, you get the decay products will, they will be gravitational signals, which will affect the microwave background of the succeeding eon. And you automatically have scale invariance because the exponential expansion of the previous eon plays the role like an inflation. You see, I didn't make the point, although I sort of almost did, because I compared the picture of inflation with the exponential expansion of an eon. Now you see, what I do is transfer that from after the Big Bang to before the Big Bang. So you do have something that looks like inflation, but it is the exponential expansion of the previous eon. You have it automatically. And so you will have these temperature variations which have a scale invariance. Also, but not quite. When I say not quite, that is because as the dark matter particles decay, they get thinned out. And when they get thinned out, you don't have an exponential, you don't have a self-similar. So you have to argue that the half-life of the dark matter particles is something a bit longer than the current age of the universe from the Big Bang. And that gives you almost scale invariance. And the observations actually have an almost scale invariance because they see what's called the spectral index, which is a slight deviation from scale invariance. And according to me, that spectral index is an indication of the lifetime of the dark matter particle. And I think that all fits together.
And what kind of Lagrangian describes your picture, I mean, eon picture? I mean, what kind of modification of gravity, even if you include matter? I would like to understand what kind of action that describes
There's
your
no
whole
modification.
picture?
Gravity is just like is Einstein's theory, and there's no difference. It's simply Einstein's general relativity. But you do, in addition, have this material which you could make it part of the picture because it is a sort of a partner to gravity, which is the dark matter. And when you cross over from one eon to the next, then the dark matter becomes dominant. But you need that to make the equations consistent when you go from one side to the next.
And
But then,
what
as
is
I
the
said,
origin of this matter in your opinion? I mean, what kind of dark matter you're
well,
explaining here?
it's a form of gravity. I mean, it's it interacts only gravitationally. It's just a scalar material which interacts. It's if you like a scalar partner to the gravitational field.
So some particle like dark matter. So I mean,
it would be particle. I'm guessing, or this needs to more theory. I'm guessing it would have something like a Planck mass,
mm-hmm.
so that the decay of the particles will be quite energetic, and you might see them in gravitational wave detectors. I'm hoping that you do, and maybe they're already seen because they would be signals that you probably wouldn't identify. You'd regard them as noise, because they would not be like the black hole collision signals. They would be probably like very sharp signals, just like a blip. But that needs more theory.
And what is the theory where you can fit this particle like dark matter, which gives to the kind of cyclic universe you're explaining? I want to understand, is it in theory or maybe some totally different theory? Yeah, I want to understand like from where the scalar comes from. So is it?
Well, it comes from you see, when you cross over from one eon to the next, you have a conformal factor. You see, usually to do the calculations, you introduce what I call a bandage metric. So you cover the crossover region by a third. You have the pre-crossover metric and the post-crossover metric, and to join them together, you have a bandage metric. And the relation between the pre and the bandage, you have a conformal factor, and then another conformal factor to relate the bandage on the other side to the next. You have a conformal factor which goes to 0 at the crossover so that you can make sense of the equations. But in doing this, you find that the equations post-crossover have an additional field. And this additional field is a scalar field. And you can write down how it interacts with things. It's quite determined by the equations. And this scalar field will have to decay, and its half-life would be roughly 10 to the 9, or no, let's see, we're now about 10 to the 11 years is what I estimate, something like 10 to the 11 years. But the decay is still, since the universe is dominated by dark matter, you would still see the pre-half-life decays, so you would see them already. And these decay products would look like gravitational wave signals, because they could only decay into gravity because that's all they are. And
if
so
I understand correctly, so the picture is you have GR and there is some scalar particle associated with it, I mean, like dark matter. Right. So then the Lagrangian that comes to my mind is something similar to mimetic gravity, what Slava Mukhanov was writing recently in the
gravity with a scalar particle. I mean, you can write these things down, but it's I don't think I could say it in words.
Okay.
Yeah, no, it's fairly well determined. Well, there are some ambiguities about how you cross over. There's some, it depends on whether the universe is spatially closed or not. If it's spatially closed, it gets rid of the ambiguities. That may be the best answer. But I mean, Paul Todd and Jörg Fraundiner and various other people have different ways of writing the equations down. So I don't want to be dogmatic about that. They do affect the issue about the dark matter a little bit. But you have to have the dark matter there, otherwise the equations don't make sense as you cross over. But you also have to get rid of it by the next crossover, otherwise you build up from eon to eon. You don't want that. So it has to have all gone by the time you cross over, and so it decays. And since it's only gravitational, it's a good guess that it would be a Planck mass particle. and the decay products would be into gravitons, because there's nothing else. It only interacts gravitationally. Sorry?
And a slightly different question: why you're not going beyond GR? Because we have a lot of indications that, I mean, like quadratic gravity comes from, I mean, basic field theory calculations, right? Like one loop corrections due to matter, R square term is natural. So
they all come from quantum mechanics, as far as I can make out. It's because you want to quantize gravity in certain ways, and you probably want to. I'm looking at it very classically. I'm not, you see, I have no idea how quantum gravity would look. Maybe you want these terms. I don't know. I don't see why. I'm not including them.
Okay.
It would depend on quantizing gravity, which is not what I'm doing here. I'm gravitizing quantum mechanics instead. You see, I think the effect that we could see in experiments is much more likely to be the gravitational effects on quantum mechanics than the quantum effects on gravity, because the effects of gravity on quantum mechanics will affect the reduction of the state. And there are certainly experiments. Well, there's one experiment already, which has been going on for a long time, which are the experiments by Dirk Baumeister. But he still hasn't got to the level of being able to detect the reduction that's expected. He has a little tiny mirror, which is about, I don't know what the experiment is doing at the moment, but certainly for a while he was looking at a mirror which was about 10 micron cube, and he hits it with a photon which is reflected back about 1 million times, and then you have to, when you get to a certain level, you might see if it's, you have to beam split the photon that hits it first of all. So beam split it first, and then half the photon, or half the wave function of the photon, hits the little 10 micron cube 1 million times, and that could be enough to displace it. And so it would be a superposition of being displaced and not displaced. And then if it reduced to one or the other, you'd see this. I think he's having some difficulties with having to cool his apparatus down very, very low temperature in order to isolate this effect. I mean, he gave a talk which I heard quite recently, and he was talking about the developments recently. But what I mean is that this is experiments which are sort of on the borderline of what one can do now, whereas experiments to test how quantum mechanics affects gravity are way off the picture, because one's usually looking for things at Planck scales and so on. And this is not experimentally close.
Okay, so a short question, if I can.
There is a question from Tomislav, maybe.
Exactly.
Yeah, I would like to ask something, Roger. First of all, I enjoyed very much your talk, but I was wondering whether anybody has investigated what happens, for example, at the end of each eon, you have to do this conformal transformation, right? So what happens, A, to the Weinberg-Stokes theorems, and B, we do know that deep infrared states obey the BMS symmetry, right? And I would naively think that this transformation should, this very deep infrared transform into the ultraviolet, that they should have a consequence, or at least predictive power of what will happen in the next eon. And my question is,
BMS, you see, because this is all without cosmological constant. All that discussion about gravitation and mass and all that stuff is all done without a cosmological constant. When you have a cosmological constant, the picture of infinity is different. You have a space-like infinity rather than a null one.
Yeah,
I don't know what the role of BMS is there. It's an interesting question. And maybe it still has a role, but it's not so obvious.
Yeah, I think it's modified symmetry. I'm not an expert. I can probably find an expert. But definitely there is also, this question has been studied.
Yeah, I don't know of a good answer though. I don't know of a good answer to the mass. You see, all that theory, which one had for the BMS group, and how you get mass and how you get the super translations and what the role they play,
exactly.
all that stuff. is modified as soon as you have a cosmological constant, because infinity doesn't look like that anymore. Infinity is a space-like surface, not a null surface. So I don't know what the role of BMS is anymore. I mean, maybe it still has a role, but you have to be careful.
I think the symmetry changes, but it is still, but I think people are investigating this precisely how to reformulate it.
I haven't seen a good answer to this question. I've heard lectures.
Thanks. Yeah.
Yes, I heard a good, very nice lecture by Abba Eshtekar where he discussed these things.
Yeah.
But at the end of it, he didn't have an answer.
I see.
I don't even know how you define mass asymptotically when you have a positive cosmological constant.
Right.
I haven't seen a good definition which replaces the BMS situation and all that. Yeah. I mean, maybe you could say it's an approximation and you can make sense of it, but it really does change the nature of infinity. In a crucial way, because I couldn't, without a cosmological constant, my scheme just simply wouldn't work. You need infinity to be space-like, which indicates that's what a positive cosmological constant gives you. And then your discussions are all very different about infinity.
Okay, thank you.
I think Ravan, now you can question if you still want.
Can I ask another?
Yeah, I don't see any other questions.
Yeah, so Roger, in your one of your slides, you're pointing some cold and hot spots in the CMB. I mean, am I correct to you're relating to the CMB anomalies, right?
They're not seen before, as far as I know. But the Hawking points, as I call them.
So they're not CMB anomalies.
The cold spot, that's much more likely to be related to the other picture, the Vahe one. You see, you have a big region, the big red region on the lower, or sort of in the middle, but just on the lower part on the right-hand side. That's huge. So according to my scheme, outside our current particle horizon, but in the previous eon, you have a very, very large concentration of material. Now that would tend to pull other material towards it, I would guess. And so you might get an explanation for the cold spot, because the cold spot is somewhere in that region, sort of on the edge of it. And I would expect, I haven't looked at it carefully and I don't know, but it's possible that you might have an explanation for some of the irregularities that people see. And the cold spot might be consistent with that, because it would thin out the distribution outside it. You see, because it's a huge matter concentration. I'm looking at the previous eon, huge matter concentration, and therefore would tend to thin out the density surrounding it. And that might mean that when it comes through to our eon, you have something, but I'd have to look at it carefully. I'm just talking off, not quite the top of my head, because I thought about it before, but it's not something that I've calculated anything about, so I wouldn't like to pontificate on it. But it could give an explanation for the cold spot. I mean, only an explanation in terms of what was there before. But it does mean that you don't have, I mean, there are lots of questions raised which are not necessarily tied to this model, because you might say that Vahe's pictures, where I had these pictures of the CMB, where you look at triples of low variance concentric rings, and you see the centers of them are very crowded in certain regions. Now, why is that on conventional theory? There's no reason why you should see that. And the crowding is very, very distinctive. And it's also, as I said in the talk, you find that it's crowded also in the color as well as in the region in space-time. And the color is an indication of the distance. So it's on the model, it's concentrated in space-time. Sorry, not in space-time, in three-dimensional space. Not only in the angular distance, but in the actual distance from us. So you see, but I mean, maybe there's some other explanation for that crowding, but I don't see any other explanation for why you should see signals of that sort, simply looking at circles of low variance which are concentric. And that's all he does. What other explanation could provide crowding of that nature? And then there's the Hawking points, and they have a very strong, the existence of them is a very, very strong signal. Maybe there's some other explanation. Sure, there could be, but I haven't seen one.
Yeah, well, there are proposals, but yeah, I agree that maybe none are very concrete, and yeah, surely it's very interesting picture you already you have presented.
And these are predictions. You see, these are predictions of the theory. I would say the clumping is not a prediction of the theory. I hadn't expected that, but the existence of these triples of low variance rings is a prediction of the theory. Also, the Hawking points is a prediction of the theory. So we see them. There are many other crazy theories about cosmology going around, but they don't have predictions which are confirmed. So I think this has to be looked at a little more seriously. Nobody seems to be looking at it seriously.
Very small remark. I am really inspired by your talk, and one thing I realize now, I should also learn drawing other than besides physics, which is very inspiring thing. I will try to draw things.
It helps because it means you've got to have a good picture of what's going on, and one can be very produce theories without sort of having a very clear picture of what's happening. And I think it's important to see that. I worry about some of these other pictures of black holes, which I can't see how to make sense of.
Okay, so it's almost 9 p.m. in Europe. So yeah, of course, it'd be nice to go ahead, but for some people, maybe it's very late, especially from people
yes.
towards Asia, for Richard especially. So yeah, I would say that officially we closed this discussion session, and it was very nice. So let's thank all the speakers of the session, of the two sessions, all the co-chairman. Was very nice, and thank you all for staying up until late. Actually, today was the latest official discussion session. So thank you very much, everyone, and see you tomorrow at 1 p.m. in Europe. Okay.
Thank you all.
Bye-bye.
Thank you, everyone.
Hello to everybody. Ciao.